deep within the underground chambers of the Atacama Large Millimeter Array in Chile. Dr. Isabella Chen adjusts the final parameters on an observation that has consumed 3 years of her career. Tonight, her international team will complete the most precise measurement of cosmic distances ever attempted, using a revolutionary technique that combines gravitational lensing, stellar parallax, and quantum interference patterns to map the three-dimensional structure of the universe with unprecedented accuracy. But as the data streams in from telescopes scattered across 6 continents, Isabella notices something that makes her question everything she thought she understood about cosmic expansion. The galaxies she's been tracking for years don't appear to be moving away from us at all. Instead, according to her measurements, space itself seems to be contracting while somehow maintaining the illusion of expansion through a mechanism so subtle and counterintuitive that it has fooled astronomers for nearly a century. If her calculations are correct, then every redshift measurement, every Type Ia supernova observation, every piece of evidence for cosmic expansion might be revealing not the growth of the universe, but its gradual, inexorable collapse toward a cosmic fate that no one has ever imagined. This shocking possibility forces us to confront one of the most fundamental assumptions in modern cosmology. Are we witnessing the expansion of space itself, or are we being deceived by the universe's most elaborate optical illusion? To understand this cosmic paradox, we must journey back to the 1920s, when Edwin Hubble first observed that distant galaxies appeared to be moving away from us at speeds proportional to their distance. This discovery, made using the 100-inch telescope at Mount Wilson Observatory, seemed to provide clear evidence that the universe was expanding uniformly in all directions. The redshift of spectral lines from distant galaxies, the stretching of light to longer, redder wavelengths appeared to be the Doppler signature of galactic recession, much like the changing pitch of an ambulance siren as it moves away from an observer. But Hubble's interpretation, while revolutionary for its time, was based on a crucial assumption: that the redshift we observe is indeed caused by the motion of galaxies through space. This assumption led directly to the Big Bang theory, the concept of cosmic inflation, and our current understanding of universal expansion driven by dark energy. Yet what if this fundamental assumption is wrong? What if the redshift we observe has nothing to do with galactic motion, but instead reflects something far more subtle happening to the fabric of space and time itself? The first hints that our understanding might be incomplete came from precision measurements of the cosmic microwave background radiation by the Planck satellite. This ancient light, the afterglow of the Big Bang itself, carries detailed information about the geometry and evolution of the universe. But when cosmologists attempted to reconcile Planck's measurements with observations of nearby supernovae and galaxy clusters, they discovered a troubling inconsistency known as the Hubble tension. Different methods for measuring the universe's expansion rate yield significantly different values. Observations of the cosmic microwave background suggest a Hubble constant of about 67 kilometers per second per megaparsec, while local measurements using Cepheid variable stars and Type Ia supernovae indicate a value closer to 74. This discrepancy might seem small, but it represents a fundamental crisis in cosmology. Our two most reliable methods for measuring cosmic expansion can't agree on how fast the universe is expanding. Dr. Adam Riess, who shared the Nobel Prize for the discovery of cosmic acceleration, has spent years trying to resolve this tension through increasingly precise observations. His work with the Hubble Space Telescope has refined distance measurements to unprecedented accuracy, but the discrepancy persists. Some cosmologists have proposed new physics modifications to general relativity, additional forms of dark energy, or previously unknown particles, to explain the inconsistency. But what if the solution is far more radical? What if both measurements are correct, but they're measuring different phenomena entirely? The cosmic microwave background might indeed reflect the properties of an expanding universe in the distant past, while local observations might be revealing something completely different about the current state of cosmic evolution. The universe might have transitioned from expansion to contraction so recently in cosmic terms that the light from this transition is only now becoming detectable. This possibility gains credibility when we consider the mysterious nature of dark energy, that enigmatic force that supposedly drives cosmic acceleration. Despite comprising roughly 70% of the universe's total energy content, dark energy remains completely undetected by any direct measurement. Its properties are inferred entirely from astronomical observations of distant supernovae and the large-scale structure of the cosmos. But what if these observations are being misinterpreted? Recent theoretical work by physicists like Eric Verland has suggested that what we interpret as dark energy might actually be an emergent property of quantum information dynamics operating on cosmic scales. In this framework, the apparent acceleration of cosmic expansion isn't caused by a mysterious repulsive force, but by the way information is processed and distributed throughout the universe's holographic structure. The holographic principle, originally developed to solve problems in black hole thermodynamics, suggests that all the information in any volume of space can be encoded on its two-dimensional boundary. If this principle applies to the universe as a whole, then what we perceive as three-dimensional cosmic expansion might actually reflect changes in how information is distributed across the universe's holographic surface. Dr. Chen's revolutionary measurement technique exploits this possibility by using quantum entanglement to probe the fundamental structure of spacetime itself. By creating entangled photon pairs and sending them to different astronomical targets, her team can measure correlations that would be impossible to detect using classical light. These quantum correlations reveal subtle distortions in the fabric of spacetime that don't show up in conventional redshift measurements. The results are startling. While classical measurements continue to show redshift patterns consistent with cosmic expansion, the quantum correlations suggest something entirely different. Space itself appears to be contracting, but in such a way that the wavelength of light is stretched to longer, redder values, creating the illusion of expansion while the universe actually shrinks. This quantum contraction operates through a mechanism that has no classical analog. In quantum field theory, empty space isn't truly empty, but filled with virtual particle pairs that constantly pop into existence and annihilate each other. These quantum fluctuations create a kind of spacetime foam at the smallest scales, where the usual rules of geometry break down and space itself becomes discrete rather than continuous. If these quantum fluctuations are somehow correlated across cosmic distances through mechanisms we don't yet understand, they could create collective effects that alter the large-scale structure of spacetime. The universe might be contracting at the quantum level while appearing to expand at the classical level, creating a cosmic double illusion that has fooled astronomers for nearly a century. Computer simulations run at the world's most advanced quantum computing facilities are beginning to reveal how this might work. These simulations model the universe as a vast quantum system where spacetime emerges from the entanglement patterns of microscopic quantum degrees of freedom. When the parameters are adjusted to match observed cosmological data, the simulations reveal something unexpected. The universe's apparent expansion is actually the classical shadow of a deeper quantum contraction. The implications are staggering. If the universe is actually shrinking rather than expanding, then our understanding of cosmic evolution, the Big Bang, and the ultimate fate of the cosmos needs to be completely reconsidered. The heat-death scenario, where the universe expands and cools until all energy gradients are eliminated, might be replaced by something far more dramatic. A quantum collapse where space itself shrinks until all matter and energy are compressed into a state of unimaginable density. But this quantum contraction wouldn't necessarily lead to a big crunch in the traditional sense. Instead of a simple reversal of the Big Bang, the universe might be approaching what theorists call a big rip, but not the kind predicted by dark energy models. Rather than dark energy accelerating expansion until it tears apart all bound structures, quantum contraction might unravel the fabric of spacetime itself, causing reality to dissolve at the most fundamental level. The James Webb Space Telescope's observations of the most distant galaxies provide tantalizing hints that this quantum contraction might already be detectable. Some of the earliest galaxies observed by JWST appear to have properties that are inconsistent with standard expansion models. They're too large, too structured, and too chemically evolved for their apparent age. If space has been contracting rather than expanding, these galaxies might actually be much older and more evolved than their redshifts suggest. Recent discoveries in condensed matter physics offer additional clues about how quantum contraction might operate. Researchers studying exotic quantum states in laboratory settings have discovered materials where macroscopic properties emerge from microscopic quantum correlations in counterintuitive ways. Some of these materials appear to expand when cooled and contract when heated, the opposite of normal thermal behavior. If similar quantum correlations operate on cosmic scales, they might cause the universe to behave in ways that violate our classical intuitions. The quantum vacuum itself might be undergoing a phase transition, changing from one type of spacetime geometry to another in a process that creates the illusion of expansion while actually producing contraction. The search for gravitational waves takes on new significance in this context. If space is contracting rather than expanding, then gravitational wave signals from distant sources should show subtle but measurable distortions that differ from expansion predictions. The Laser Interferometer Gravitational Wave Observatory and its European counterpart Virgo are collecting data that might already contain evidence for quantum contraction. But detecting these effects requires analysis techniques that haven't yet been developed. Advanced machine learning algorithms are beginning to reveal patterns in gravitational wave data that don't match theoretical predictions based on expanding spacetime. These anomalies are subtle, tiny deviations in the frequency evolution of merger signals that could easily be attributed to instrumental noise or modeling errors. But when analyzed collectively, they might be revealing the first direct evidence that spacetime itself is contracting, while creating the illusion of expansion through quantum mechanisms. The cosmic microwave background radiation, that ancient afterglow of the Big Bang, might also contain hidden signatures of quantum contraction. The tiny temperature fluctuations that we observe across the sky were created by acoustic waves propagating through the hot, dense plasma of the early universe. But if space has been contracting rather than expanding since that time, then these fluctuations might encode information about the quantum contraction process itself. Dr. Chen's quantum measurement technique is beginning to decode these hidden signatures. By using entangled photons to probe the polarization patterns in the cosmic microwave background, her team can detect quantum correlations that would be impossible to observe using classical techniques. These correlations suggest that the early universe was already undergoing quantum contraction, but at such a subtle level that it appeared as expansion to classical observers. The implications for our understanding of time itself are profound. In a contracting universe, the arrow of time might not point in the direction we think it does. What we perceive as the forward flow of time, from past to future, might actually be the reverse direction on cosmic scales. We might be living in a universe that is running backward, approaching its beginning rather than its end, with quantum contraction creating the illusion that time moves forward. This temporal inversion could explain many of the puzzles that plague modern cosmology. The fine-tuning problem, why the fundamental constants of nature appear to be precisely calibrated for complexity and life, might be resolved if the universe is actually evolving toward these conditions rather than away from them. We might be witnessing not the random emergence of complexity in an expanding cosmos, but the inevitable approach to a quantum singularity where all possibilities converge. The search for dark matter might also be fundamentally misguided if the universe is contracting rather than expanding. The gravitational effects that we attribute to invisible matter might actually be consequences of quantum contraction distortions in spacetime geometry that create the illusion of additional mass when interpreted through the lens of expansion cosmology. Recent experiments at particle accelerators around the world have failed to detect any of the hypothetical particles that supposedly comprise dark matter. Decades of searching with increasingly sensitive detectors have yielded no evidence for weakly interacting massive particles, axions, or any of the other proposed dark matter candidates. If these particles don't exist because dark matter is actually a misinterpretation of quantum contraction effects, then the entire enterprise of dark matter detection might be searching for something that was never there. Advanced civilizations, if they exist, might have already discovered the truth about cosmic contraction and learned to exploit it for purposes we can barely imagine. Instead of struggling against the apparent expansion of the universe, they might be working with quantum contraction to achieve forms of space travel and communication that seem impossible under expansion cosmology. Quantum contraction might allow instantaneous communication across cosmic distances through entanglement correlations that operate outside the normal constraints of spacetime. If space itself is contracting, then quantum information might propagate along contraction channels that bypass the speed of light limit. Advanced civilizations might use these channels to maintain communication networks that span entire galaxies, connecting their outposts through quantum correlations rather than electromagnetic signals. The possibility of time travel also takes on new dimensions in a contracting universe. If quantum contraction is moving us toward the cosmic past rather than the future, then travelers who learn to navigate contraction currents might be able to reach earlier epochs in cosmic history. The universe might be filled with temporal explorers from advanced civilizations who have learned to surf the quantum contraction waves backward through time. But perhaps the most profound implication of cosmic contraction is what it suggests about the nature of reality itself. If our most basic assumptions about space, time, and cosmic evolution are completely wrong, then we might be living in a universe that is far more mysterious and counterintuitive than anyone has ever imagined. The very concepts of past and future, cause and effect, might need to be reconsidered in light of quantum contraction dynamics. Standing in that underground control room in the Atacama Desert, watching data stream in from telescopes around the world, Dr. Chen realizes she might be witnessing the most fundamental paradigm shift in the history of science. The universe might not be the expanding, cooling, aging cosmos that we've assumed for nearly a century. Instead, it might be a quantum system in the process of contracting toward a state of infinite possibility, a cosmic compression where all potential futures converge into a single, inevitable outcome. The evidence is still preliminary, and the implications are so radical that they challenge every assumption about cosmic evolution. But if quantum contraction is real, then we're not living in a universe that's running down toward heat death, but in one that's winding up toward a quantum crescendo of unimaginable complexity and beauty. This possibility transforms our understanding of meaning and purpose in cosmic evolution. Rather than temporary patterns of organization in an expanding, cooling universe, we might be essential participants in a cosmic contraction process that's moving toward greater complexity, higher consciousness, and deeper understanding. Every scientific discovery, every work of art, every moment of love or wonder might be contributing to a cosmic convergence where all possibilities become actualized simultaneously. The universe might not be dying, but being born, not expanding toward emptiness, but contracting toward fullness. And we might be living witnesses to the most beautiful paradox in cosmic history, a universe that appears to be growing larger while actually becoming more concentrated, more connected, and more conscious with every passing moment. In our quest to understand cosmic expansion, we might be discovering that the universe is actually teaching us the deepest lesson about the nature of reality, that sometimes the most profound truths are hidden behind illusions, so convincing that it takes quantum vision to see through them. The great cosmic contraction might be the universe's way of showing us that even our most fundamental assumptions about space and time are just the surface layer of a deeper quantum reality that defies all classical intuition.